Designing a robot that can make decisions on its own is a pretty scary prospect, especially when we're talking about something as big as a car going 60 miles an hour. But if you can design a system that's safe and effective, the payoff is huge. People are already buying self-driving vacuum cleaners as well as lawnmowers that will cut the grass and then go back and park themselves. Imagine a drone that flew over your crops and took pictures of your property on a daily basis. There are obvious military and police applications as well, with some drones taking off while others are coming back to charge. All of this can be done automatically if you can design a system that's up to the task. Now, I am always looking for ways to get my kids excited about engineering, so I immediately started thinking, what if I made a kid-sized self-driving car? That would be incredible, and it would get my kids excited about this technology. I started this project by buying an old beat-up go-kart so that me and my kids could take this thing apart and restore it back to new health together. I did all that work only to figure out that that go-kart was way too small for my son. Not only that, I thought it would be better if my two younger children could both ride in it together, so I ended up just getting a new cart instead. To pull off a project like this in my home shop, a lot of different skills need to come together. Not only do we need mechanical design, but we're going to need a multitude of sensors to detect our environment. We need to receive GPS information to know where our location is. We're going to need electronics to take all of this data in and process it. And finally, we need artificial intelligence to actually make decisions about which way to go. Clearly, we won't be able to cover all of this in one video, so we're going to break this up into a series. Because this project relies heavily on microcontrollers and programming as well as mechanical design, I've recruited one of my favorite YouTubers to help me out with this project. I'll tell you more about that later in the video. So let's start with baby steps. How do we take a machine that was designed to be driven by a person and make it so that a computer can drive it? Not only does the computer need to be able to turn the steering wheel, it needs to know how far it's turned the steering wheel. So let's start there. If we're going to replace the human driver, then obviously a lot of things need to happen. First, we're going to ignore the fact that the driver has to make decisions while operating the vehicle. We'll save that topic for another video. My goal is to focus on the mechanical problem. How do I get a computer to steer this vehicle, take over acceleration, deceleration, and braking? One of the first things I want to do is remove the gasoline engine and make this an electric vehicle. Not only is that going to simplify the controls, but it'll also be quieter. I don't have to handle gasoline and things like that. Of course, that doesn't mean I couldn't control a gasoline engine with the computer. I could certainly take control of the pedals with electric actuators, and gasoline engines definitely have their benefits, but I'm going to lean towards electric on this project. So let's focus on the steering problem for a moment. Here's a better look at our steering column. It looks like we have some sort of rack and pinion inside of here, and then those rods continue out to the side over there and right here. And when I turn the steering wheel, as you can see, it pulls on this rod and moves the wheels. So we have several different places that we could try to actuate this wheel, but of course motors are designed to spin and our wheel spins. So I think the simplest solution is to grab onto this column somewhere in here with an electric motor and some sort of gear ratio, which will allow us to spin this shaft and then spin the wheels. I'm going to take a whole bunch of pictures of this steering column and probably model out just enough of this so that we can get started on designing the steering mechanism. This is the motor I'm thinking about using. This comes off of an old beat up power wheelchair. So my son and daughter can still sit in here. It shouldn't interfere with anything on this side where their legs will be. Attaching a motor is not going to be enough though. We need some sort of way of knowing how much we've actually turned the steering wheel, and we'll figure that out with a potentiometer. So let's go jump into CAD software and start figuring out how we're going to mount our potentiometer as well as our electric motor. Well, crap. I didn't even consider that these would be made in such a way that you couldn't use something different. That's what I get for thinking I was finding a good deal. My hope was that there would be some kind of set screw here which would allow me to disconnect this shaft from this, and then I could just put something else with the 5mm shaft in there. But clearly I was mistaken. As you can see, part of the planetary gear is right here on the motor. Man, that really sucks because now I need a different solution. That's press fit on there, and I don't want to mess with that fit and have this slip. Well, wait a minute. So basically what I need to do is couple this shaft to the gear output on this. My current design calls for a coupler to connect whatever shaft comes out of here, which I assumed was 5mm, and connect it to this, which is 1/4 inch or 6.35mm. So those parts have already been ordered, they're on the way. But if that shaft is 5mm, and it probably is, we can confirm that. It is. Perfect. So maybe what I'll do is disassemble this, cut that shaft. Hopefully there's enough room to give me just enough to hold on to with the coupler. And then I just need to be sure that the spacing is right so that these gear teeth mesh with the gear inside of there. Okay, so I need to take some careful measurements here. Okay, here we go. Well, if you ever wanted to see inside a stepper motor, here you go. Look at that. That is just beautiful. Love engineering. So I need to cut it off right in here somewhere. All right. Whenever your back's against the wall in the shop, almost any problem can be solved with a grinder or a hammer. I think this will work. There's a flat plate in here that this will rest up against. So that's pretty good. And the forces in here are very low. We're just talking about enough to rotate the potentiometer. Certainly this may break apart and fail, and then I'll just have to come up with another solution. But the cost on this was so low, it's worth giving it a shot. So I'll connect my shaft coupler here. That ought to allow me to rotate this, and you can see the output shaft moving, so we're definitely in business. All right. Not what I was going for, but hopefully that'll work. The plan is to drive the steering wheel with a chain and sprocket like you would use on a bicycle. What I like about that is there won't be any slip because of the teeth and the sprockets, but one of the issues I'm going to run into is that this is not, a proper shaft. It's actually just a pipe. To make sure that I don't get any slip between this pipe and the sprocket, I want to use a taper lock bushing, which is what this is. So essentially this guy will fit inside of this hole, and as you tighten the two screws right here, this wedges itself tighter and tighter, pinching those two sides together against the shaft. In my opinion, is one of the best options when you don't have a keyed shaft. So that's what I'm going to be using here. But there's another twist to this. This pipe with the paint measures at 16.5mm, and you can't buy a bushing at 16.5mm. And the closest thing I could get was this 16mm bushing, which obviously won't work. It's a little bit too tight. Or I could go up to 18, which is too loose, maybe put a shim or something in there. The plan is just to use this 16mm bushing and open the hole up just a little bit on the mill so that it'll slide over the paint, but still give me a good clamp whenever I wedge these two pieces together. Man, that actually almost looks kind of good. Hey, there we go. All right. Let's tighten it all the way down, and we'll be back in business. One of the last things we need to do for the steering mechanism is to measure how far we've moved the steering wheel. And that's what this mechanism is all about. So here you can see the coupling that I was describing earlier. This is the gear output, and you can see that coupling spinning. What it's doing is turning this potentiometer. As we turn this shaft, this potentiometer is going to be changing the voltage output on this cable, somewhere between 0 and 5 volts. Or actually, it might be 0 and 3 volts. I'm going to let Bill decide on that one. Whichever voltage we use, we're going to slice that up into tiny little pieces. This particular potentiometer is a 10-turn potentiometer, but the steering wheel only rotates about 2/3 of the way around. And that's where the planetary gear comes in. The planetary gear is going to multiply the input by about 14. And that way I can get something very close to the full range on this potentiometer from a very small turn of the steering wheel. At the end of the day, we're going to get a much higher resolution, and the computer will know very precisely how far the steering wheel has turned. Final step is just going to be to mount this guy here, and this is the piece of angle iron I plan to use. This will be mounted somewhere like this, and essentially I'm just going to cut 2 slots in this plate on a milling machine. This is one of those moments where you wish you could rewind the clock just 30 seconds. Look at this. Here you can see I'm tightening the last little sprocket, and look at that. I cracked it. The problem is I tightened it too much. As you can see, there's almost no gap left here. It shouldn't be quite that small. And because I over-tightened it, it broke the actual gear here. What's frustrating about this is not that I'm going to have to order another part. It didn't cost very much. The problem is I can't test my project until the new parts come. And that's really frustrating to lose all this time waiting for stuff that you ordered. Boy, look at that crack. Right through the face of the gear. This has probably been hardened. Just not gonna take the weld. Oh man. Yeah, it's cracked on the inside as well. All right, ladies and gentlemen. I think this guy's done. Let's jump online and order some parts. I have an idea. I've already ordered replacement parts, but I don't really want to wait. So I'm going to drill a hole all the way down through here and then pin this to the steering column. That way I can still remove this because that's a critical part of being able to assemble and disassemble all this. And if it doesn't work, then I just have a small hole in the steering column. So we're going to load this in the mill and hopefully this will work. All right. That's certainly good enough for testing. Let's talk about how we're going to get a computer to take over control of this mechanism. And for that, I need to introduce you to the DroneBot Workshop. Bill is the host of one of my all-time favorite YouTube channels called the DroneBot Workshop. He covers everything related to microelectronics and sensors. You guys have been calling me the Bob Ross of mechanical engineering. Well, this is the Bob Ross of electronics. If you want to learn electronics at a level that anyone can understand, Bill is going to be the guy to help you do it. Bill and I have been talking for several years now, but when I started thinking about the challenges of a self-driving car, I knew Bill was going to be the guy to help me push this thing over the finish line. I know Bill is going to do an amazing job explaining the programming side of things and the electrical components. So I'm going to focus on the mechanical challenges. But there's one area of crossover that I want to cover here, and that is speccing out the motor for the drivetrain. Now, I've made a whole video about how to size a motor, and I'll put a link in the description of this video. But briefly, all I did was take a fish scale and pull on the steering column to see how much force was required to actually get the steering wheel to rotate. Once I had that number, all I had to do was figure out how fast I wanted the steering wheel to turn and how far. From there, I could figure out my gear ratios and so on. But I described that in great detail in the other video, so I'm gonna let you check that out in the description. While working on this, I also made a prototype that I sent to Bill. That way he'd have something that has the same type of motor, the same sort of gear ratios and connection between the potentiometer and the motor, and we can anticipate any problems that might come up, since he'd be working with very similar hardware. All right, let's get back to wiring this guy up. I've wired everything up according to Bill's instructions, and I'm just reading through his email now, confirming that I'm doing it correctly. At this point, we're almost ready. I have tested the servo input. That's working perfectly. I've also tried to test the potentiometer input, but I'm getting some weird behavior there. After tinkering with this for a while, I finally decided to just take the potentiometer out, and it's almost immediately obvious the problem. I broke another potentiometer. I thought I had aligned them carefully enough that I wouldn't quite get all the way to the end of the movement, and clearly I did. I decided to go ahead and order like 5 of these, and I'll try to load the next one a little more carefully. Hopefully my parts will arrive tomorrow night, and we can get this all wrapped up. In the meantime, I'm gonna go think about something else. At this point, I've figured out a system for installing the potentiometer without breaking it. It only took a couple tries. Now I've got the potentiometer working, and all of the other individual components seem to be working. But I still can't get this system to come together. So I spent hours troubleshooting, trying to get this thing to work. I finally just decided I am not seeing the problem. All right, I gotta call in my pinch hitter, because this is clearly, can't talk and type at the same time. This is clearly not working, but I am so close. I have to be overlooking something stupid. And there he is. Hello?
Hey, Jeremy.
How you doing, sir?
Not too bad, how are you?
I am almost there. I feel like I'm missing something silly here. Can I put you on speakerphone? I'm recording everything, just so you know.
Yeah, no worries.
Okay, 1 second. So everything is connected right here. Here, you can see what I'm reading from the Arduino.
Well, you've got a PWM reading, right? Yeah, PWM out. And the motor, you say, isn't moving at all?
So let me show you. So we spend the next hour trying to troubleshoot this problem, but Bill actually says something pretty important at about the 30-minute mark.
What if you had somehow inadvertently blown the output of the shaft, but internally it was still working? I mean, we could try moving to a pin other than 6, but that really makes no sense.
After another 30 minutes of troubleshooting, it turns out indeed both pin 5 and 6 had stopped working. So we moved those to 3 and 4, and then we were back in business.
Oh, I was just wondering if I was just trying to figure out how something like that could have happened. Did you by any chance accidentally ground that at some point, or?
There's a good chance I did. I've done all kind of stuff here in the last day or so trying to get it working. We have power on the system. Turning the knob. Whoa! God. Man, that was fast. Okay. Whew. All right, let me let my heart rate slow down. Wow. That was scary. We retested all the individual components and everything seemed to be responding properly. So now it's time to put the chain back on and test the whole system fully connected. Oh man, please work this time. It's gotta work this time. Is anything I'm forgetting? Oh boy. All right, here we go. That was a good sign. So we should be dead center. Okay. Okay, maybe we finally got something here. Oh, come on. Well, that's weird. Okay, so we're like 90% of the way there. What? I broke the steering column. I'm pretty sure that this guy should be in line with that guy. Wow. At first I thought I broke it, but I actually just bent it. This does bring up an interesting safety question though. Would I want this kind of failure while the car was in motion? My gut tells me no, you wouldn't want to catastrophically break your steering column while the vehicle was moving. I could just downsize the electric motor so that I don't have quite so much torque. In other words, when this sort of failure happens, the motor will be overloaded instead of having enough torque to actually rip the steering column up the way it did. But then the motor would fail, and in both cases, I've lost control of the steering. Either it's electronically I've lost control of the steering and it may go somewhere unpredicted, or I broke the steering column and it's mechanically steering in the wrong direction. In either case, I've lost control of the steering. So I think there's more things to think about there. My gut tells me it's actually cheaper to replace the steering column than to replace the motor. I'd love to know what you guys think about that. It's an interesting problem because it's not just the cost factor. There's several things happening there. All right, I think we're gonna finish this autopsy tomorrow. I'm gonna go play with the kids, it's game night, and I need to order parts anyway, so I think we might be done. This morning I had an epiphany. It's amazing what a good night's sleep will do for you. All right, here's the deal. The motor is spinning the wrong direction. To confirm my suspicion, I reviewed the tape this morning, and even though the camera view is not great, I can definitely tell that a small change in the position on the input led to a huge correction on the steering. And that's what I would expect. You see, the more correction that you need to make with the steering, the higher the speed of the motor. And as you get closer to the position you're supposed to be in, the motor should slow down. What I was getting was the opposite. And that's because the motor thought it was at the wrong extreme and thus was giving me a higher correction. This thing is totally destroyed. I tried to start taking it apart last night, and I'm gonna need to cut this to actually get everything apart. And I also need to order a new steering column. So this video is definitely done for now. I would feel so much better if I could hook everything up and just confirm my hypothesis is correct, but I'm about 98% sure that that's what went wrong based on what I saw. So hopefully this will be a quick repair and we can jump right onto the drivetrain in the back. We'll turn this into an RC car next to make sure we can steer it remotely, and then we'll let it drive itself. Anyway, thank you for joining me through all this pain and suffering, and I'll see you in the next video. Thanks for watching.